This week's lecture is on magnetism. Next week we will have a two-part lecture on electronic devices. There are objects in nature that have natural magnetic properties. This is a rock found in the ground that has a natural magnetic property that allows it to hold on to this wrench. These rocks are called lodestones. They have an inherent magnetic property. These rocks are made up of something called magnetite, which is also called black iron oxide. Its formula is Fe3O4. When a rock formation has a sufficient amount of this material in it, it will demonstrate or show magnetic properties. Magnets have two ends. Each end is called a pole. All magnets have poles, and in these poles is where the magnetism is concentrated. You do not detect magnetic fields throughout a particular magnet, only on the ends or the poles. The one end is called the North Pole. It is called the North Pole because it seeks the natural magnetic north. The end opposite to that end is called the South Pole. Now, it's important to understand that if you cut a magnet in half, you don't end up with one half of it being the North Pole and the other half of it being the South Pole. If you cut a magnet in half, then each half has both a North Pole and a South Pole. This slide demonstrates what's known as the law of magnetic poles. It is analogous to the law of electrostatic charges. In this law, unlike poles are attracted to each other, and like poles are repellent of each other. Here you see two north poles that are brought into proximity with each other. The one north pole will repel the other north pole and cause the free swinging magnet to swing away from the other magnet. Each magnet generates what's known as a magnetic field. A magnetic field is the region around the magnet in which other objects are affected by the magnetic attraction. This diagram shows what's known as lines of flux. Lines of flux, much like lines of force in the electrostatic chapter, are imaginary lines that indicate the direction and strength of the magnetic field. When one draws the lines of flux, the concentration of lines, that is the number of lines per area, demonstrates the amount of strength of the magnetic field. The arrow demonstrates the direction of the magnetic field. And it is convention to show the direction as being from North Pole to South Pole. And as you see in this bar magnet, these lines of flux wrap around so that they come around from the North Pole to the South Pole. If you wanted to show a doubling of magnetic strength, then you would, in this diagram, you would show, instead of 6 lines in the same area, you would show 12 lines. Or up here, the same thing. The other law that is analogous to the laws of electrostatic force is the law of magnetic force. The law of magnetic force states that the force between two magnetic poles is directly related to the product of the pole's strength and inversely related to the square of the distance between them. This is the formula for the law of magnetic poles. F represents the force, kappa represents a constant, P1 is the strength of one magnetic pole, P2 is the strength of the other magnetic pole, and D is the distance between the two poles. What you see here is that the form of this equation is very similar to the law of gravitational force, in which you have m1 m2 over r squared, and the law of electronic force, or electric force, which is q1 q2 over d squared. These laws show a natural consistency in nature with these various natural forces. There are several different phenomena that occur related to magnetic force. One phenomenon is known as permeability. A material can be highly permeable, and that is, it can absorb and channel the lines of flux, or it can be impermeable, in which it does not absorb or channel the lines of flux. The diagram on the right shows something called magnetic shielding. Magnetic shielding occurs is when the permeability of a substance traps the lines of flux and prevents them from entering a particular area that is shielded. What you see here is iron, which is a highly permeable substance. The magnetic field is heading in direction of this iron circle, and the permeability of this iron is quite high, so the lines of flux are absorbed into the iron, and the central area is shielded from the lines of flux, so that if you were to be sitting in here, for example, you would not experience any magnetic field. Now, the greater the permeability, or the higher the permeability, the more likely it is that this material would become magnetized. Once it leaves the permeable substance, they spread out and even out until they reach the South Pole. Now, one property that's true about permeability and shielding is the idea as to whether a substance increases or decreases the magnetic force in a particular area depends on its placement. For example, in a situation like this, if you were in this area, you would actually experience more flux because of the focusing of the magnetic flux by the permeability of this iron bar. But if you were within this area or in this area, you would experience no magnetic force and no magnetism because you would be shielded. So whether or not shielding occurs depends on whether or not or where you are in relationship to the permeable substance. On a microscopic or molecular level, how magnetism is generated is related to the charged particles in the molecules. Probably the most important aspect or phenomenon that develops or causes magnetic fields is the motion of electrons. Now, there are actually two ways in which electrons can move. They can move around the nucleus like this, and then they can also spin. One thing you notice here is that each of these are shown as to having a magnetic field. Two of them are north and one of them are south. And this is because each of these electrons are assumed to be spinning. And when you have an odd number of electrons, it's generally accepted that one of them will be spinning in an opposite direction to the other two. What happens is when you have two electrons that spin in opposite directions, they cancel each other out, so the overall effect is to not have any magnetic field generated. But when you have an unpaired electron, such as over here, these two may cancel each other out, but you're left with one that allows for the generation of a magnetic field, at least at this molecule. Now, motion of the nucleus itself, spinning of the nucleus itself, can also be related to the generation of a magnetic field. As I said before, spin is the most important cause of magnetism in magnetic substances. These two diagrams are demonstrations of how spin affects and generates a magnetic field. This one shows counterclockwise spin. This one shows clockwise spin. When you have opposite spin like this, you see that your north and south poles are on different sides of the electron. So you have on this side a counterclockwise spin the North Pole here, the South Pole here. On this side you have a clockwise spin. The North Pole is now up here, the South Pole here. Now if these were the only two electrons available, these two would cancel each other out, and the overall effect would be to have no magnetism at all. So the strong magnetic field is produced by the spin of the electrons on their axis. A weaker magnetic field is generated by the motion, orbital motion of electrons around the nucleus, which I pointed out to you on the last slide. An even weaker form is by the spin of the nucleus, which contains positive charges. Again, the most important is this spin of the electrons, which leads to the generation of strong magnetic field. Weaker magnetic fields come from the motion, orbital motion of electrons around the nucleus, and the weakest aspect, or the weakest contribution to magnetic force or effects, comes from the spin of the nucleus itself. These various atoms and their spinning electrons, spinning nuclei, and orbitally traveling electrons arrange themselves in something known as domains. A domain is a group of atoms which have aligned themselves into a single magnetic field. On both sides you see red and blue. The red is to represent north, the blue to represent south. And each of these represents, as it were, tiny magnets within the material. Now, if these domains exist, they are used to explain what's known as the domain theory of magnetism, which states that the magnetic field of a magnet is the sum of thousands of these domains, each domain containing a group of atoms whose electrons have aligned themselves in such a way as to generate a magnetic field. So a magnetic substance can only form a magnet if its domains are aligned in such a way as they don't cancel each other out. So on this side, you have unaligned or loose random domains, and this substance would show no magnetic effect. This substance, on the other hand, because the domains have lined themselves up, would demonstrate a magnetic effect. Now, if you applied some physical force or agent upon this so that you jumbled these domains and led them to become like this, then you would see this magnetic material to lose its magnetic effect. Conversely, if you applied a magnetic field to this and caused them to line up this way, you would essentially magnetize that material. This is a summary of the three types of materials in terms of their magnetic reaction to magnetic attraction. The least attracted to magnetic attraction is called diamagnetic material. In these materials, it is thought that the electrons of the atoms of these materials all have paired spins, such that they all cancel each other out. Because they have paired spin, they have or do not demonstrate any attraction to magnetic material. The intermediate substance is a substance that has atoms that maybe have one unpaired electron per atom. Because of this unpaired electron, there's a magnetic effect, but it is weak. And so diamagnetic material, examples are chromium and aluminum, have some attraction to magnetic material, but very weak attraction. Some examples, by the way, of diamagnetic material include copper, gold, silver. If you put a magnet close to these substances, they are unaffected. The third type of substance is ferromagnetic material. These are substances that have several unpaired electrons per atom. These several unpaired electrons result in many unopposed magnetic domains. These are thus strongly attracted. Examples of this include iron, nickel, and cobalt. Now, in each of these category, in the category of ferromagnetic materials, materials can either be soft or hard. And what does that mean? What that means is the ability for these materials to be magnetized. And a magnetically soft material is a ferromagnetic material that can be magnetized fairly easily. It can be magnetized in a weak magnetic field, but it does not hold that magnetic field very well and results in what's known as a temporary magnet. A temporary magnet is any magnet that's formed from magnetically soft material, and it does not keep, it's called temporary because it does not keep the magnetic effect over a period of time. The opposite of a soft or magnetically soft material is a magnetically hard material. Magnetically hard materials are materials that are attracted by magnets. They resist the change that comes from a magnetic field, but once they are magnetized, they are relatively permanent. They're difficult to magnetize, but once magnetized, they hold their magnetic field for a long period of time. And this results in what's known as a permanent magnet. A magnet is made from a magnetically hard, a permanent magnet is made from a magnetically hard substance that retains its magnetism over a long period of time. There are various ways in which magnetic materials can be magnetized. One way is by direct contact. This is called magnetism or magnetized by contact, and basically the magnet, it touches the ferromagnetic material and there's a transfer of magnetic effect. Most people believe that what happens is that the domains within the unmagnetized material line up because of the magnetic effect of the magnet and then thus become magnetized or align themselves and generally become magnetized. These magnets can be permanent in the case of a hard magnetic material or temporary in the case of a soft magnetic material. You can also magnetize by induction, and what that means is that you can generate or magnetize a material by putting it in a magnetic field without actually touching the magnet. The closer it is to the magnet, the better or the more likely it is to magnetize the material. The last way to magnetize a material is to put it, or to put an electric current through around the material. Electric currents, when they flow through a conductor, always generate a magnetic field, and this magnetic field can affect the ferromagnetic material that it's wrapped around. What happens here is when the current goes through these wires, it generates a magnetic field that's oriented in this direction, and it can magnetize the central material inside. This is a diagram to represent an electromagnet. An electromagnet is a coil of wire that is used to generate or to create a strong magnet when current is passed through it. The way an electromagnet is made is that a central area known as the core is wrapped with a conducting material, and then electric current can be passed through this conducting material, and when the current is passed through this material, it leads to the formation of a magnetic field, which affects the ferromagnetic material in the middle, and that becomes a magnet. The strength of the magnetic field is determined by two factors. The most important factor is the current that goes through the wire that's wrapped around the core. You will remember the current is the number or the amount of electrons that pass through this surface area or through this wire over a certain period of time. 1 amp being 1 coulomb of charge per second. If you increase the current you will increase the field that's generated and you will increase the strength of the magnet within. The other way that you can increase the strength of the magnet is to increase the number of wrappings of this wire around the central core. The greater the number of wraps, the stronger the magnetic field that's generated. And so there's two ways when you create an electromagnet that you can make a stronger magnet. One is to increase the current that goes through the wire. The other is to increase the number of wraps around the wire, around the core, excuse me. I actually gave this as a project, a science project, to a student, where I had him do an experiment where he counted the number of wrappings around the core and measured how much weight the magnet could pick up using a standard current. There are also a couple of ways that a magnet can lose its magnetism. This is called demagnetization. Permanent magnets do not lose their magnetism very easily. However, they can lose their magnetism. The single most common way in which a magnet loses its magnetism is by heat. If you heat a magnet up to a certain point, the domains will spontaneously disorganize and the magnet will cease to be a magnet. The point at which in any particular material will lose its magnetism is called the Curie point. This is the temperature that a ferromagnetic material loses the magnetism by because it loses its domains. The other way to make a magnet lose its magnetism is by striking it very hard with a hammer or some other hard object. Significant trauma can cause a magnet to lose its magnetic effect. Both of these make clear sense when you think in terms of the domain theory of magnetism. Magnetic fields can also impact charged particles that pass through them. This is a diagram showing a stream of electrons that would normally, without the presence of a magnetic field, would normally go straight across to the other side of this bulb. However, this beam of electrons is deflected because it passes through this magnetic field. The field is called a deflecting field. The force in the magnetic field that causes the electrons to change their direction as they pass through that field. When this occurs, this is called magnetic deflection. And so when a charged particle, principally an electron, but to a lesser extent a proton, passes through a magnetic field, it is deflected or deviated from its path and ends up going in a different direction. The last section of this talk will be on the magnetic effects on the Earth, and the Earth is a magnetic field, or the magnetic fields in the Earth. First of all, we have to talk about a compass, or a magnetic compass. A magnetic compass is a device that consists of a magnet that's allowed to swing freely in the horizontal plane. Now, frequently this device is used for navigation, but it doesn't necessarily have to be used for navigation. The key here is that the device contains generally an arrow or a needle. This arrow or needle is magnetized, and the second important part is that it's allowed to rotate freely in a horizontal plane. When those two things happen, then this magnet will point in a particular direction. Now, it will point to what is called the magnetic North Pole. However, the magnetic north, or what it points out as north, is actually geographically north. It functions as south. Remember, the law of magnets says that opposite poles attract. So the north aspect of your magnet within the compass is going to point toward the magnetically south part of the Earth. the magnetically south aspect of the Earth is geographically north. So it's called North Pole, but it's actually magnetically south. And that's what's shown up here. You have a geographic north. It's functioning as the south pole of this magnet. The geographic south functions as the has a functional north magnetic pole. And so your compass will point toward this north, and that's the geographic north. The magnetic north and south pole do not correspond exactly to the geographic north and south pole. What that means is the precise point that the compass points out is not exactly due north. It's a little bit off. And we'll talk about that some more in the next few slides. Here you have the what I was just talking about. You have the geographic north here and the magnetic north here. And the difference between these two is called the magnetic declination. So the Earth's magnetic poles are called north and south due to their geographic location, not because of their magnetic properties. The angle of declination is the angle between the true geographic north and the magnetic north that the compass indicates. So you have true north here, magnetic north here. And in this case, the true north is a few degrees east of the magnetic north. And you'll notice that you're sort of in the western part of the United States. And so if your needle points in this direction, you realize that you're a few degrees, your true north is a few degrees to the east of that. Now this angle varies depending on where you are on the Earth, even where you are in the United States. If you're over on this side, then instead of being to the east, it's actually slightly to the west of true north. And that's shown on this slide. This slide shows the various declination angles depending on where you are in the United States. Now, each one of these lines is called an isotonic line. An isotonic line is a line on the map. If you're on this line anywhere on this line, then your angle of declination is 5 degrees east. If you are anywhere on this side, these solid lines, your angle of declination is west. And so, for example, if you're on this line, your angle of declination is 5 degrees west, which means your arrow is pointing 5 degrees west of true north. And you have to take that into account. Now in the middle here you have something called the agonic line. The agonic line is actually the line where all the angle of declination is 0. All the compass points where all the compass points point to true north without any angle of declination. Now, in addition to horizontal deviations, we also have vertical deviations. What I mean by vertical deviations is that the magnetic field does not travel parallel to the surface of the Earth. It actually comes up from below the surface of the Earth. And this was first discovered by the use of something known as a dipping needle. A dipping needle is a needle on a compass that allows the needle to deviate vertically. And sometimes if you've used a compass, you might have noticed that the needle will deviate vertically one direction or another. This is an example of a dipping needle. And so this needle is not only pointing north, but it is also pointing down at an angle of about 45 degrees. So what that means is that this represents the surface of the planet, and so that means that the magnetic field is actually coming up from the ground at an angle of 45 degrees from the surface of the planet. Now, that angle is called the angle of inclination. The angle of inclination is the angle between the Earth's magnetic field and the surface of the Earth. It's this angle right here. This angle becomes very important, particularly if you're flying, because the higher you are, the more this is affected, and it affects your compass readings. Now, similar to the isotonic lines, the isoclinic lines are lines that correspond to the isotonic lines, except they're vertical and they show where the angle is equal to a certain amount. And this is an example of some isoclinic lines. If you're on anywhere on these lines, then your angle of declination is the same anywhere on this line or on this line. I can't read the numbers there, but let's say that this is maybe 30 or 20 or 30 degrees, if you're or 40 degrees. If you're standing in this area right here, the magnetic field anywhere on this line will be coming up from the ground at an angle of about 20 or 30 degrees. Now, the important is this one right here in the middle, which I'm going to show you in more detail on the next slide. This next slide shows this is the isoclinic line of 0. The isoclinic line of 0, that is where the angle of inclination is 0. That is where the field is actually parallel to the Earth, is also known as the magnetic equator. If you're standing on the North or South Pole, your angle of inclination is exactly 90 degrees, which means it points right straight into the ground. Which is why if you're standing on the North or South Pole, the needle just spins around in circles. Conversely, if you're on the equator, the inclination angle is now 0. And this line encircles all the way around the Earth and represents halfway between the North and South poles at any particular point. Now you'll notice the line is not straight. That's because the magnetic north is not true north and the magnetic south is not true south. Now, as it turns out, the magnetic field effect caused by the Earth does not just affect the Earth, but actually has an effect into space. The extent to which a planet's magnetic field extends into space is called the magnetosphere. The shape and size of the magnetosphere is affected by solar winds. So, solar winds are streams of plasma, streams of electrons and cations that emanate from the sun. So the sun is over here and they are in this direction, and you notice the side in which the solar winds are is smaller than the side where they do not exist, and the shape is different between the two sides. The boundary for the magnetosphere is called the magnetopause. Beyond that boundary, there is no magnetic effect of the planet on the space beyond that point. Now, as it turns out, the magnetosphere has a significant impact and a significant physical effect on the Earth. The big effect is something called Van Allen radiation belts. The Van Allen radiation belts are belts of radiation, belts of high-speed charged particles that are trapped within the magnetic field, within the magnetosphere. They occur when high-speed particles come from the solar winds and become trapped within the magnetic field of the Earth. There's actually 4 of these belts. There are 2 inner belts on either side of the planet, the sun being either on this side or this side, and then there are 2 outer belts. Now, when these plasma particles become trapped, they collide with molecules in the atmosphere, and they result in these shimmering lights that you see, particularly in the northern part of the northern hemisphere and the southern part of the southern hemisphere. And these are called the aurora. In the north, they're called the aurora borealis, or the northern lights. In the south, they're called the aurora australis, or the southern lights. And they're a shimmering display that occurs because high-speed particles collide with air particles and shimmer or radiate. And you can see those particles. Now, as it turns out, the Earth is not the only planet that has a magnetic field. There are other planets that have magnetic fields. The most important of those is Jupiter, and Saturn. And here's a picture of Jupiter with its northern polar ice cap and the little red spot, also called the giant red spot. Here's the Earth over here, and Jupiter has a fairly large magnetic field associated with it. And it's actually quite important in terms of the effect that it has on bodies that pass through our solar system. The other magnets are stellar magnets, and by the term stellar, we're talking about stars. And various stars, like the sun, have magnetic fields. Now, the most important thing about, and most important difference between stellar magnets and planetary magnets is the fact that planetary magnets, including the Earth's magnetic field, are very stable. In other words, where the field lines are, where the North Pole is, where the South Pole is, etc., those things are stable. In a star, because of the composition of a star and how a star generates its magnetic field, it is extremely unstable and fluctuates violently. And this diagram shows that in one time period you might have field lines that head north and south. In another time period you'll have field lines that are more squiggly and going in this direction. Another time you may have field lines that are more east to west almost. And this instability is what characterizes stellar magnets. This completes our lecture on magnetism. As I said, the next two lectures will be on electronic devices. And I want to thank you for your attention on this material.